Hey, what's up math friends? Today we are beginning a series of videos that will prepare us for chapter 4 of FLM, Franco-Lepofsky and Merman. We have put that on the back burner for a while because we've had a lot of stuff, other stuff to do, but it's time to discuss untwisted vertex operators. There's a couple of technical points that I thought deserved a little bit more attention, and specifically when we go into talking something as complicated as the untwisted vertex operators, we kind of really need to focus in a little bit more on the untwisted Heisenberg algebras. So there's a little bit of housekeeping to do. Also, this little pause gave me a chance to go back through FLM and kind of investigate it a few more times. And I gotta say, it's really beautiful exposition. The way they treat everything is, I mean, I think there's one author that I don't really jive with. I don't really understand what he says when he writes, but for the most part, the line of argumentation is gorgeous. And it just gets better every time you go through it. So first, let's review what an ideal of a Lie algebra is. It's a subset of the algebra such that, like, if you take a commutator of any element of the Lie algebra with any element of that subset of the Lie algebra, you get another element in that same subset. Okay? So the particular ideal that we'll be interested in today is the so-called commutator ideal, which is literally the set of all elements that can be represented as a commutator of two other elements in the Lie algebra. A little funny, right? Just a little. A Heisenberg Lie algebra is defined to be a Lie algebra whose center is given by the commutator ideal, with the additional constraint that the dimension of the center must be 1. Did you get that? Now, it's meant to simulate, I guess, what Heisenberg originally came up with, which is something that can be reduced to the commutator of x with p is equal to, I h bar from quantum mechanics. Before we go any further, let's prove some fun facts about Heisenberg algebras. To start with, let's restrict our attention to finite dimensional Heisenberg algebras. Okay, fun fact number 1. The dimension of a Heisenberg Lie algebra is necessarily greater than 1. Proof. Consider a Lie algebra of dimension 1, then we know that it is necessarily an abelian Lie algebra because that is true of all one-dimensional Lie algebras. So therefore, the commutator subalgebra of a one-dimensional Lie algebra is necessarily trivial. That is to say, it's 0. So it cannot have dimension 1, and so therefore it is not a Heisenberg Lie algebra. Fun fact number 2. Heisenberg Lie algebras necessarily have odd dimension, assuming they're finite dimensional. Proof. Since a Heisenberg algebra is necessarily more than one-dimensional, consider first the center, so that's one dimension. Right? Now, consider another vector, v, from the Heisenberg algebra that's orthogonal to the center. The commutator of v with the center is, by definition, 0. So we can already see that the two-dimensional span of that vector v with the center is not a Heisenberg algebra. Indeed, we need to add a third vector, let's say w, that's obviously orthogonal to v, else a commutator with v would be 0, and obviously orthogonal to c, because, by definition. So there must be a third, if you like, dimension, such that the commutator of v with w is proportional to c. That is to say, it's in the center. Awesome. So if the span of now w, v, and c are not equal to the original Heisenberg algebra, we can iterate this process, pick another vector, then you'll need another vector that you can commute with so as to get another element of the center. And so you can see right away that vectors necessarily come in pairs. So pairs plus the central element gives us a 2n plus 1 dimensional Lie algebra. So indeed, yes, finite dimensional Heisenberg Lie algebras are odd of dimension greater than 1. Fun fact number 3, we can always decompose any finite dimensional Heisenberg algebra H into the direct sum of 3 billion Lie subalgebras. Let's call them H0 plus H plus H minus. Proof. First, we can identify the center of the Heisenberg algebra with H0, no big deal there. Okay, so we have, if you like, for a 2n plus 1 dimensional Heisenberg Lie algebra, we have now 2n dimensions left to contend with. Following the algorithm that we used to prove the second fun fact, you can kind of see how this is going to go, right? So take 2 orthogonal elements that are not in the center of the Lie algebra H and take their commutator. Let's say V and W. And of course, let's assume that their commutator is not 0. Good. So if the commutator of V and W is positive, then we assign V to H plus and W to H minus. If it's negative, we assign them oppositely. Good. And following the algorithm, again, that we used for the proof of the second fun fact, we can iterate this procedure all the way down until we have n vectors in H plus and n vectors in H minus. Good. And so put differently, the commutator of any let's say W plus from H plus with any W minus from H minus gives us a element in the center, and by the way, that's a positive constant out in front. Really tedious, I'm sure. So why are we doing this? We're doing this because it naturally extends to the concept of a grading and kind of shows you why we need to think about gradings in the first place anyway. We should have started with that. You might recall that a grading on a vector space is just some set and then we assign linearly independent subspaces of that vector space to members of that set. Ostensibly that's kind of boring, so usually what we want to do is, instead of having a set, we want to have like a group, an abelian group operation, like, I don't know, the integers or some rational numbers, fractions, or even a field like the complex numbers. You can have a complex graded vector space. That's no big deal. And why do we do that? We do that because we want to talk about graded algebras. And so, for example, a graded Lie algebra has a structure that for, say, x m, for some element x, which has a homogeneous degree m, and some element y, which has homogeneous degree n, we can talk about the commutator of x with y and demand that any non-zero commutator between those two have homogeneous degree m plus n. And that's basically the structure. You remember this. But later, it's super interesting that kind of group structure on the homogeneous degrees is really important. It becomes really important, particularly for untwisted vertex operators. Why do we care about Heisenberg Lie algebras? Well, that's a great question, but as a physicist, I care because they are useful in representing quantum operators, that is to say quantum mechanics, that is to say things that we study. So, for example, for the typical example, we consider the harmonic oscillator algebra, right, with a dagger, and 1. 1 plays the role of the central element here. It's just the number 1. And a dagger are 2 operators that we get from kind of rotating position and momentum together, and a with a dagger is equal to 1. But of course, in quantum field theory, we extend this definition considerably because we want to talk about maps from space-time, let's say, R 1, 3 to the reals, say for a real scalar field, some physical entity that exists in all of space and time. And we want to talk about the quantum mechanics of an object like that because they describe particles like pions, that kind of thing. How do we do that? Well, we Fourier transform that field, right? And then we can consider the Fourier modes, the coefficients of the Fourier modes as operators. And those operators are either going to be of the form A or a dagger. And now we grade the space of said operators by, by a vector in kind of Fourier space, this not a position vector like x, but like the opposite of x, like a wave vector, a vector that would describe a wave, like the dual lattice, if you like, associated to the lattice of points in a discretized version of space-time. But anyway, yeah, that's the Heisenberg Lie algebras of infinite dimension that we are typically interested in studying. Okay, hopefully that jogged your memory a little bit. Next time, we'll review modules for Heisenberg algebras, and we'll point out some extra fun facts about them. Great. Thanks so much for watching.